Hi, I'm Sarbjit Singh from quantfinancecourses.com. Welcome to Quant Problems, Episode 1. Today, we're going to derive the well-known trader's approximation for the price of an at-the-money call or put option. We will derive this in two ways. Method 1. We will use a Taylor expansion on the cumulative normal function. Method 2. We will assume the stock is normally distributed at expiry, rather than the usual assumption, which is that the stock is log-normally distributed at expiry. If you like the content, subscribe to my channel, hit the like and the notification bell if you would like to be notified when I post another video. Enjoy! Let's get down to business then. This approximation is derived under the assumption of zero interest rates and no dividends for the stock process. The option price approximation is given by 1 divided by the square root of 2 pi times S, the current stock price, and sigma, the volatility of the stock, times the square root of big T, the expiry time of the option, minus little t, which is the current time. The term inside the square root is the remaining time, which we can show with a simple diagram. As we said in the introduction, the first approach to get this approximation is to use a Taylor expansion on the cumulative normal function. This is the formula of a call option in the Black-Scholes framework. The first term is the discount factor. Remember, we have deterministic interest rates. The second term is the forward, that is the expected value of the spot in the risk-neutral measure, conditional on the information at little t, which is the current time. N is the cumulative normal function, and d1 has its usual meaning. d1 equals log of the forward divided by the strike, plus half sigma squared times the remaining time, all divided by the standard deviation of the stock return, which is sigma times the square root of the remaining time. We then subtract the strike, x, times the cumulative normal of d2. We can write d2 simply in terms of d1. It is d1 minus the standard deviation. Okay, so we know that the price approximation formula works equally well for an at-the-money put option as well as an at-the-money call option. We will derive it for a put option. We don't have to remember the Black-Scholes formula for a put option. We can use put-call parity to derive it from the call option formula and the price of a forward contract. A short animation will illustrate put-call parity. That simply says a call minus a put has the same payoff as a forward contract, which is the spot at expiry minus the strike. So the price is the expected value of this, conditional on ft in the risk-neutral measure, appropriately discounted, squeezing in the discount factor here. What does that equal? The expected value of the spot at expiry, conditional on ft, is just the forward. So writing the discount factor first, times the forward, and the second term is a constant strike, which is straightforward. So what we do now is take the expression for the call option price, plug that into here, and solve for P, the put option price. So what does that give us? It gives us the put option price is the discount factor multiplied by the strike times 1 minus n of d2 minus the forward times 1 minus n of d1. We can simplify this 1 minus nd2 term and the 1 minus nd1 term. nd2 is the cumulative normal density function at d2, and it is the integral of the normal density function between minus infinity and d2. So if we plot the density function here, excuse the rough drawing, this is the PDF here, the familiar bell-shaped curve. N of x0 is the area to the left of x0 here. And if we want 1 minus n of x0, since the area in total is 1, this is the area to the right of x0. And by symmetry, it's also the area to the left of minus x0. So we can write 1 minus n of x0 equals n of minus x0. Substituting this in to our formula for a put option gives the following. We now have these two expressions for a call option and a put option, respectively, in the Black-Scholes framework. Now let's put in the actual assumptions from the problem. Interest rates are 0, there are no dividends, so the forward is equal to the current stock price. And the strike is the same as the current stock price since the option is at the money. The astute amongst you will notice that the at the money call option price and the at the money put option price are the same. This is the case when the strike equals the forward. D1 and D2 in both formulae are close to each other in practice, so this is where we will use a first order Taylor expansion to simplify them. To do this Taylor expansion, we need to write down the definition of the cumulative normal function as an integral. Nx is the integral of the normal density function from -infinity to x, which means that the derivative of n is simply the normal density at x. Writing d2 in terms of d1, let's do the approximation for the put option formula. N of minus d2 is n of minus d1 plus sigma square root of the remaining time. The first order Taylor expansion essentially assumes the function is locally linear. We will do the Taylor expansion about x equal to minus d1 and delta x equal to sigma square root of the remaining time. The derivative of n with respect to x is evaluated at minus d1. Let's remind ourselves what d1 actually is. Plugging in the forward equals the strike equals the current stock price gives log 1, which is 0. The whole expression evaluates to half sigma square root of the remaining time. Performing a Taylor expansion on the exponential function here, disregarding sigma squared and higher order terms, means this is approximately 1. Now, if we plug this approximation for n minus d2 into the put option pricing formula, this now gives s times sigma square root of the remaining time times 1 divided by the square root of 2 pi. This is exactly what we were trying to show. Okay, let's look at the second method, where we assume the stock at expiry is normally distributed. Under the standard Black-Scholes assumptions, the stock is actually log normally distributed at expiry, which means the term here in the exponential is normal, where z is a standard normal with mean 0 and variance 1. Let's write the mean and variance of the stock at expiry. This is the mean if you don't have any dividends, which is just the forward. And the variance is the forward squared times e to the sigma squared times the remaining time minus 1. Let's assume the stock at expiry is normally distributed with the same mean and variance, with the assumptions of the problem plugged in, i.e. rates are 0. So the mean is just the current stock price, and the variance, if you perform a Taylor expansion on the exponential to first order, is s squared sigma squared times the remaining time. I prefer to work with the standard normal random variable, so let's rewrite the stock at expiry as the mean plus the standard deviation times z, which is a standard normal variable. Now we have the distribution of the stock price at expiry, we can calculate the put option price. The value of the put option is the expected value of the payoff at expiry, the maximum of the strike minus the stock price and 0. That's what this notation with the plus sign means, which we can write as an integral from minus infinity to infinity, substituting in the current stock price for the strike of the payoff times the probability density function. Let's pull out the constant terms, and this is looking a lot like the solution that we are after. We plug in the normal density function here. On the next line, we will take out the 1 over square root of 2 pi term, The integrand is non-zero when z is negative, so we integrate from minus infinity to 0. And we see that we have an exact differential here. Minus z is the derivative of minus z squared over 2 with respect to z. So finally, we will evaluate the integral between the limits of minus infinity and 0, which gives us 1 divided by the square root of 2 pi times the current stock price times sigma times the square root of the remaining time times 1 minus 0. Substituting in st equals s, we have the same solution as we did for method 1, as we can see. And it is the same solution we had at the beginning. Perfect.